I wanted to take a moment to talk to you all about adiabatic cooling. And you're going to see a good diagram coming up after this, but I wanted to just kind of talk through it a little bit. So there's this process that occurs where, and you can see on the screen here, I drew sort of a grassy area and there's a tree, so you can see we're outside. And I drew this little pocket of air right down there at the ground. And we're going to imagine that this is a separate pocket of air. It's really just mixed in with all the rest of the air. But just for a moment, I want you to pretend like there's like an imaginary boundary around this little pocket of air. Okay. And what happens is this air is, depending on what temperature it is and depending on how stable the atmosphere is, this air has a chance to rise up, to go up into the air, to go up higher into the air, I should say, or higher into the atmosphere. Now, in the background, I want to point out something that I drew over here on the left-hand side, which is what's called the environmental lapse rate. So it's going to take me too long to write that one down, but I'll just say it again, environmental lapse rate. And what that does is it tells you the sort of the pattern of temperature drop as you move up into the atmosphere. Now, the environmental lapse rate can change based on where you are. It's always going to be different. In this particular example, I just showed an environmental lapse rate that shows that the temperature drops 20 degrees Celsius per 1,000 meters. So every 1,000 meters that you go up, the temperature drops 20 degrees. So in this case, that is, I'll just write it out, the environmental, I'll just abbreviate it, lapse rate. So it's the rate at which the temperature lapses or drops in the environment. Now, like I said, the environmental lapse rate can change based on which location you're at. There is a different type of lapse rate that does change based on your location. And that is what is known as the dry adiabatic lapse rate. I'll write that one down. Okay, so the dry adiabatic lapse rate says that anytime you have a pocket of air, like the one that I drew down there on the ground, that's 82 degrees, anytime you have a pocket of air and it rises up 1,000 meters, it's going to drop by exactly 10 degrees Celsius per 1,000 meters. Okay? That is a fixed number. That number is always the same no matter where you are. The dry adiabatic lapse rate does not change. So, in this particular case, notice that our pocket of air is at 82 degrees. Now, I just realized I drew this in Fahrenheit, so you're going to have to pretend with me a little bit, but you're hopefully still going to get the idea. In this particular case, we're going to pretend like Fahrenheit and Celsius are the same, and I know that's totally wrong, but the most important thing here is to get the concept. So you've got a pocket of air on the ground. It's 82 degrees. The environmental air is 80 degrees. So that pocket of air is warmer than the air around it. So it's going to want to rise because hot air rises, right? So that 82 degree air, it rises up 1,000 meters and it gets to this middle point here. And now the air has dropped by 10 degrees, again, pretending we're at Celsius here, by 10 degrees. So now we're down to 72. Okay? Well, the surrounding air is at 60 degrees. So 72 is now a lot warmer than 60, so the air is going to continue to rise. In fact, it'll probably rise even faster. It goes another 1,000 meters, and it gets up to 62. So you see it's dropping by 10 each time. The environmental lapse rate is, in this particular example, dropping by 20 each time. But again, that part can change. The dry adiabatic lapse rate cannot change. Now, last but not least, I just wanted to give you a concept to think about, and you'll see this a little more clearly in the diagram that comes up next. So again, that pocket of air down at the bottom, we said is 82 degrees. And every pocket of air, no matter where you are, contains some water vapor. Even if the air is really dry outside, there's always some water vapor in the air. Well, you saw from the video, and you know from what we've studied before, that if the air expands and the air cools off, the moment the air cools off, you're going to start to, or if the air cools off enough and it reaches the dew point temperature. Remember, we talked about that before. So if the air cools off and reaches the dew point temperature, all of a sudden, you're going to have a situation where some of that water vapor starts to condense, starts to become liquid. Now, at that point, when that happens, think carefully about this. If we start to form liquid droplets of water in this parcel of air, then that means that, so if we walk this through, that means that the water vapor lost heat, right? So in other words, the water vapor became liquid water, and that heat was given back to the air. So if you think about the fact that the water itself had to lose heat to become liquid, that means the heat is given back into the air, sort of added back to the air. So what happens is then you get, when that occurs, when you start getting those droplets of water, you get something known as the moist, or sometimes referred to as wet, adiabatic lapse rate. And that can vary. That can be anywhere between 4 degrees Celsius to 9 degrees Celsius per 1,000 meters. And so what ends up happening then is normally, if the air is just moving up and there's no condensation and no liquid water forming, the temperature is going to drop 10 degrees for every 1,000 meters, right? Air goes up 1,000 meters, drops 10 degrees. What we're saying is that when liquid water starts forming in that parcel, some of the heat is actually given back into the air. So instead of it dropping or losing 10 degrees, it's going to lose less. It's going to lose 4 degrees to 9 degrees per 1,000 meters instead. So anyway, this is just a quick summary of the three different types of lapse rates. Environmental, which again changes based on the location. The dry adiabatic lapse rate, which is always the same, 10 degrees Celsius per 1,000 meters. And the moist adiabatic lapse rate, which can change based on how much humidity and whatnot you have. And that ranges from 4 degrees to 9 degrees Celsius per 1,000 meters. So continue to read on and take a look at the diagram that I show you next, which has much better artwork than mine, and hopefully you'll get a good feel for all this.